We are starting Chapter 2. Chapter 2 is an introduction to functions. Now, functions are just a fancy word for a relationship of x and y, equations. You've done a lot of functions before, you just haven't called them functions. This chapter can get a little confusing, but once you understand the basics of functions, it clears everything up when you start graphing and doing more with functions. So section 2.1, using graphs to relate to quantities. We first have to take into consideration what a graph means, and that's the most important thing. Can you look at a graph and interpret what it's talking about? So in the Solve It problem, which is going to be on page 97, we're going to look at this graph. This graph is the Solve It. The graphs below relate the height of the water to the volume of the water in each container. Which graph goes with which container? Justify your reasoning. Now, I'm not asking you to draw this all down, but I do want you to make note. If you want to sketch these shapes and what the graphs represent, the arrows, this is what we're relating. So the first thing we're notice, we're relating the height of the water to the volume of the water in each container. So it's very important to understand what we're doing in these graphs. Now, I have my little cursor here so you can kind of see what we're looking at. In each of these, the x-axis is the volume. Now, the reason why we only have the first quadrant is because this is only talking about positive x and positive y. We're relating volume to the height. So as volume goes to the right, what is happening to the height? Well, let's look at our first example. So as we're going to the right, we have a constant rate right here of the height of the water in the container going up. And then all of a sudden, the height starts slowing down. In the next one, we have a gradual increase that's constant as we fill the container with water. Over here, as the volume goes to the right, as the volume starts filling up, the height of that volume increases at a constant rate. Now, if you're looking at the last two, you'll notice that the first, which is the second one here, the first of the constant rates gradually increases. The last one actually increases at a much faster rate. So let's look at our shapes. If we would fill this first one up, this one right here, let me use my red. So we're looking at that one. If we're filling that up, what can you tell me about what's happening? Now we're relating the volume. We want to know, as the water goes in, how does that relate to the height? Well, we know it's going to be constant because the shape of the container does not change. So we know it's going to be the second graph or the third graph. But what do you notice about the height? The height is not very tall. So if we look at the second graph, we know that the height is gradually increasing, but it's not nearly as tall as the third graph. So we know that this first container goes with the second graph. The second graph goes with the first container. Now let's look at the second container. Well, this one also increases. If we're filling it with water, the height's going to increase at a constant rate. But the height is much taller because the container is taller. So therefore, the third graph is going to go with the second container. And then lastly, we have a container that starts increasing, and it's going to go pretty fast, but then it widens, and as it widens, the height's going to slow down. And that's going to be our first graph. Our first graph is going to go with the third container. And it's going to take some time. If you have questions or kind of confused about relating graphs, it will take time. You have to really slow down and interpret what the graphs are asking you. So if we look at the shaded box in the middle of page 97, it says, as you have noticed in the Solve It, the change in the height of water as the volume increases is related to the shape of the container. Here's your essential understanding. You can use graphs to visually represent the relationship between two variable quantities as they both change. So let's look at the problem 1, analyzing a graph, the got it questions. You will notice that you have two different graphs. You have an A and a B. One is board length and one is June's cell phone costs. So here's what the got it asks. It asks, what are the variables in each graph? Describe how the variables are related at various points on the graph. So I want to know, how are these variables related? You have to explain in words what's going on here. But first, let's look at this problem. You don't need to write it down, but let's read it. The graph shows the volume of air in a balloon as you blow it up until it pops. What are the variables? Describe how the variables are related at various points in the graph. So the variables are just looking at the two quantities that are related to each other. So the two variables are volume and time. So let's look at what's happening. So before we do anything, just let's look at and analyze the graph. As time goes on, what's happening to the volume of the balloon? It's increasing. So it's important to note that the volume increases each time you blow air into the balloon. But let's think of what happens here. So let's see, you start blowing air in the balloon. What happens here? You blow air into the balloon. What happens here? You blow air into the balloon. What happens here? Well, you're not going to constantly keep blowing air in the balloon because you have to stop and take a breath. So each of these sections, right here, right here, and right here, are when you take time to pause to breathe. And then the increase is when you're actually blowing air. So what happens in the middle of the fourth blow? So here's where you blow air the first time, blow air the second time, blow air the third time. What happens right here? Well, what do you notice about the volume? It automatically goes down to 0. So that means the balloon completely deflated. So what happened? The balloon popped. So when the balloon pops in the middle of the fourth blow, the volume decreases to 0. And that's exactly what we're doing. So the question is, describe how the variables are related at various points on the graph. Well, you start increasing by blowing air into the balloon, you take a breath. Blow air into the balloon, take a breath. Blow air into the balloon, take a breath. Start blowing air, and then it pops. So that's how you start relating one variable to the next. So let's look at the board lengths. So I'm not going to draw this because it's in your book. So if you look at A, what are the variables? Well, the variable will be relating time versus length. So what do you think is happening? You have a board, and all of a sudden the board length, bam, gets cut. It gets cut again. So what's happening, I will draw it. So let me draw this. Alright, so we have our little graph. If you notice right here, as time goes on, the length of the board doesn't change. So that instantly, the length gets smaller. It remains that same, and then it gets smaller again. Gets smaller. So what could be happening here? Well, the length of the board remains constant for a time before another piece is being cut off. So what's happening here is, if you were describing how these are related at different points, is someone's cutting the board. The board remains a certain length, and bam, they cut it with a saw. And then it remains the same, they cut it again. So that's what's happening. The board length is being cut shorter and shorter every time. And then at the end, there's no more cuts. So let's look at B, June's cell phone costs. What are the variables in each graph? Well, the variables are minutes of calls and cost. So what do you notice here? Minutes of calls. Minutes of calls. What do you notice about the costs? It stays the same. But then we hit this point. What happens at this point? The cost starts going up. So what do you think is happening? Well, your cell phone carrier gives you a number of minutes, and the cost remains the same. Let's say you get 500 free minutes. And then all of a sudden you start going over those minutes, and what starts happening? The cost starts going up. So the cost remains constant for a certain number of minutes and then starts increasing. All right, look at practice A and do 1 and 2 on your own if you want to. If you don't want to, no big deal. Just fast forward this section here. But if you want to do 1 and 2, pause the video and look at them. Well, 1, it relates the variables as number of pounds and total costs. As the number of pounds increases, the total cost goes up. At first quickly, and then it starts slowing down. Number 2, the variables are the area painted and the amount of paint in a can. Now if you think about it, you're going to have a big area that's not painted and a lot of paint, and as you start painting, the area you paint gets smaller, as does the amount of paint in a can. So the more you paint, the less paint is left in the can. And you are using the paint at a constant rate. You'll notice that you're constantly using the paint at a constant rate. It's not slowing down or increasing, but it's a constant rate all the way until you've painted the entire region. This example you do not need to write down, but we're going to start matching a table and a graph. So multiple choice. A band allowed fans to download its new video from its website. The table shows the total number of downloads after 1, 2, and 3 days, and 4 days. Which graph could represent the data shown in the table at the right? So look at the table at the right. Day 1, day 2, day 3, day 4. Day 1, 346. Day 2, 1,011. Day 3, 3,455. Day 4, 10,426. A, B, C, or D. Which one looks like it could be a representation of the table? So let me first ask you some questions. These will make you think. Should the horizontal distance between the points shown in the correct graph be constant? Horizontal distance. That would be this, the number of days. Should it be constant? Yes, it should, because the increase in the day column is always going to be 1. The day always increases by 1. So the horizontal distance, we're not talking about vertical distance, the distance between each red dot should be the same because the days are increasing by 1. Should the vertical distance between the points shown in the correct graph be constant? No, because the total downloads, which represents the vertical axes, are not constant. So that means we can mark off A, because if you look here, this makes a straight line. We don't have that. This is not a constant increase of total downloads. The next question. Would a graph of only the new downloads each day be similar or different from the graph of the total downloads each day? It would be similar to the graph of the total downloads because the increase in the number of new downloads each day is always going to be greater than the previous increase. It constantly increases as the days increase. All right, so let's look at it. We start off with a number. It increases by about 700. Then it increases by about 2,500. And then it increases like 7,000. So what do you notice about the increase each time? It's getting higher and higher. Therefore, graph B would be our answer. The total number of downloads increases each day, and each increase is noticeably greater than the previous increase. So the graph should rise from left to right, and each rise should be steeper than the previous rise. The correct answer is B. I want you to do the got it problem where it's talking about sunscreen. Do that one on your own. Now, what do you notice about the number of uses? That's your x-axis. It increases by 1. As it increases by 1, what's happening to the amount of sunscreen? It's decreasing, but here's the most important part. Is it decreasing at a constant rate? Yeah, it does. Because we go from 5 to 4.8. That's a decrease of 2/10. It decreases each time by 2/10. So it's decreasing at a constant rate. So here's the question. Is it going to be A or C as your answer? Because both A and C are decreasing at a constant rate. It should be C, and here's why. If you notice A, A decreases at a constant rate. But what do you notice about the amount of sunscreen left by the last use? It's on the axis of 0. So it says we don't have any sunscreen left. But after our 3 uses, our table shows that we have 4.4 ounces left. Therefore, your answer would be C. I want you now to look at practice A, and I want you to match the tables to the graphs. If you did it correctly, number 3 would be C, number 4 would be A, and number 5 is a constant rate, so that would be B. So it's CAB. Here's another example. Now they're going to give you a situation, and you actually have to come up with your own graph. A model rocket rises quickly and then slowly to a stop as its fuel burns out. It begins to fall quickly until the parachute opens, after which it slowly falls back to Earth. Draw a sketch that could represent the height of the rocket during its flight. Label each section. So, we know we're representing what 2 variables? Time, because as time goes on, what's happening to the rocket, and height. So let's first draw our 2 axes. So we have time, which we're going to say in seconds, because we wouldn't want to do hours or minutes, because we're talking about a rocket in air, and then height in feet. So let's start graphing what's happening here. It says a model rocket rises quickly. So we can start off rising quickly. And then it slows to a stop. So right here the height stops because it doesn't go up anymore. Then it starts falling quickly. But then the parachute opens. Well, what happens when a parachute opens? It's not going to fall as rapidly. But then it falls at a constant rate until it falls back to Earth. So, let's graph what happened here. We have to label our sections. What's happening here? Well, it started rising quickly. And then what happens here? Well, the rocket stopped climbing. That's when the fuel burned out. So right here, it stopped or stops rising. And then it starts falling quickly. And then what happened right there? The parachute opened. And then what happened in this last line? It fell at a constant rate. So then it falls at constant rate, or you could say it falls slowly. But there we just represented each part of that graph that was told to us in our situation, in our problem. All right, now I want you to look at the got it sections. You can be done. If you understand everything to this point and you think you could draw situations, you can be done. But I want you to do A and see if you can get it right. So do A, read it to yourself, pause the video, and then come back and see if the graph matches what I'm going to draw. Here's what your graph would look like. Remember, you're always going to be off the ground a little bit because it's a swing. So you swing farther off the ground and then back down. Swing a little higher, you get farther off the ground, back down. You notice we have a constant line because the swing's always going to be the same distance when it's at its lowest point. And then all of a sudden, we get higher in the air, and then you slowly stop the swing. So it starts going back down, you're swinging less, and then you're back down.